In my last video, I made a blue gas called trifluoronitrosomethane to expose a fake photo on Wikipedia. If you saw that video, you already know the problem. The gas I made was blue, but it didn't really match what the literature said. According to the papers I found, it's supposed to be a deep blue gas. Mine was more of a light blue, almost cyan. My sample back then was not perfectly pure, so there was always this annoying possibility in the back of my mind that the pure gas might actually be a deeper blue. I also mentioned that in the caption of the picture I uploaded to Wikipedia. But let's be honest, who actually reads image captions on Wikipedia? And I know, in the video I said that I believed the color would not change much if the gas were perfectly pure. But belief is not the same as proof. To make things worse, I got a comment from a viewer who said that his colleagues had worked with this gas over 30 years ago, and he remembered it as being more intensely blue. All of that slowly started to eat away at me. What if the pure gas actually is deep blue and I'm the one spreading misinformation? Honestly, that's not something I could just ignore. So, I decided to do the only sensible thing. Make the gas again using a different synthetic route, clean it as much as I possibly can, and finally settle once and for all what the color of this gas really is. Last time I made trifluoronitrosomethane by shining UV light on a mixture of trifluoroiodomethane and nitric oxide. That works, but it has some drawbacks. Most importantly, if you want to produce larger amounts of gas, you need a very large flask. The method I'm showing you today can, in principle, be scaled up much more easily so that you could make larger quantities of the gas. At least in theory. As you will see, in practice it turned out to be much less straightforward than expected. The plan was to first make this molecule. It's called trifluoroacetylnitrite and it can be directly converted into the blue gas. To make it, I first need this part of the molecule, which comes from a highly corrosive and toxic yellow gas called nitrosyl chloride. Nitrosyl chloride is one of the compounds that forms when you mix nitric acid and hydrochloric acid to make so-called aqua regia, which is strong enough to dissolve gold. However, since I needed pure nitrosyl chloride, I could not simply use aqua regia. Instead, I had to use a different method to produce the pure gas. For that, I needed another toxic gas, nitrogen dioxide. When this gas reacts with potassium chloride, it forms nitrosyl chloride and potassium nitrate. But how do you make a gas react with a solid on a larger scale? Here's what I did. I took a long glass tube. At the bottom, I connected the NO2 cylinder. Inside the tube, I would pack potassium chloride and a bit of glass wool at the bottom keeps it in place. Before filling the tube, I had to moisten the potassium chloride with about 2.5% water. So I put portions of potassium chloride into a mortar, added a small amount of water and ground everything thoroughly. As you can see from the UV reactor sitting in the fume hood, I was doing all of this in parallel with the synthesis route from the previous video. At that point, I was not sure whether that first route would actually be successful, so I wanted a backup running at the same time. After mixing the potassium chloride with water, it was no longer a dry powder, but a slightly sticky mass. I then packed it into the glass tube, making sure the filling was as even as possible so that the nitrogen dioxide would react uniformly along its length. The final setup looked like this. Nitrogen dioxide flows from the cylinder into the bottom of the tube, passes through the potassium chloride and reacts to form nitrosyl chloride and potassium nitrate. At the top of the tube, the nitrosyl chloride comes out and is led into a gas washing bottle filled with calcium chloride to dry it. The dry nitrosyl chloride then passes into a cold trap that is cooled to about -75°C, where it freezes out. Behind the cold trap there is a second gas washing bottle filled with calcium chloride to prevent moisture from the air from entering the cold trap and reacting with the nitrosyl chloride. Once the entire apparatus was set up, I placed a dewar filled with the cooling mixture under the cold trap and slowly opened the gas cylinder. You can see the orange-brown NO2 flowing into the tube. As soon as it hits the potassium chloride, the color fades and turns yellowish. You can even feel the outside of the tube getting warm from the reaction. Slowly, the whole tube fills with yellow nitrosyl chloride. After a while, the gas reaches the first gas washing bottle. Here you can clearly see the color difference between nitrogen dioxide and nitrosyl chloride. The NO2 going in has a more brownish red color, and the nitrosyl chloride coming out is clearly yellow. After drying, the nitrosyl chloride condenses in the cold trap as an orange-red liquid. The color changes are actually very useful. You can see the reaction front crawling up the tube, and it tells you exactly where the potassium chloride has already been consumed. It is important to stop the reaction before the NO2 reaches the top of the tube in order to avoid contamination of the nitrosyl chloride with NO2. This reaction takes quite a while, so in the meantime I started making the second compound I needed, silver trifluoroacetate. And I made it starting from this silver bar. Even though it looks very nice, I had to turn it into a brown powder, silver oxide. To do that, I first had to prepare silver nitrate. So I placed the bar in a beaker, added a bit of distilled water and then nitric acid. At first, not much happened. You could only see a few bubbles forming on the metal surface and the acid turning slightly yellow. To speed up the reaction, I decided to heat the beaker on a hot plate. After a short time, the reaction became much more vigorous and brownish red fumes started to rise from the beaker. Those are nitrogen oxides, mostly nitrogen dioxide. Yes, the same gas I was using to make nitrosyl chloride. Once the silver bar had completely dissolved, I left the solution to cool overnight. By the next morning, beautiful silver nitrate crystals had formed at the bottom of the beaker. From there, I could finally make silver oxide. I filled a large bottle with distilled water and added sodium hydroxide. After it had fully dissolved, I slowly poured the silver nitrate solution into the bottle while stirring. Immediately, a brown solid started to form. That is silver oxide. Once all the silver nitrate solution had been added, I stopped stirring and let the solid settle to the bottom. Then I poured the liquid through a filter, making sure not to pour too much of the solid into the filter at once so it would not clog immediately and slow down the filtration too much. Once the liquid was removed, I rinsed the solid thoroughly with distilled water to wash out any leftover sodium hydroxide. To dry the silver oxide, I put the wet product into a vacuum oven. As the name suggests, it is an oven that you can evacuate so that water is removed quickly. After about a day, I had nicely dried silver oxide. From this, I could finally make what I actually needed, silver trifluoroacetate. In a round bottom flask, I added distilled water and slowly dripped in trifluoroacetic anhydride. It reacts with the water to give trifluoroacetic acid. I could have used the acid directly, but I only had the anhydride on hand. To this acid, I added the freshly made silver oxide. In a neutralization reaction, silver trifluoroacetate and water are formed. After I had added all the silver oxide, I had to remove the excess acid and water. So I connected the flask to the vacuum line through a cold trap. The water in the flask evaporates and freezes out in the trap. If you look in the background, you can still see the nitrosyl chloride synthesis running. Once the silver trifluoroacetate was completely dry, I transferred it from the flask into a jar for storage until I needed it. In theory, it should have been white to slightly gray. In my case, it was brown, because I also had to use some older, impure silver oxide, since the amount I made myself wasn't enough. That was not a big problem though, because the next reaction would clean it up anyway. Now that the silver trifluoroacetate was ready, it was time to check on the nitrosyl chloride. And it looked like I had collected enough for the next step. To temporarily store the nitrosyl chloride, I decided to condense it into a smaller vessel. That was absolutely the main reason, and not at all the fact that I had forgotten to weigh the empty cold trap, so I had no idea how much nitrosyl chloride exactly I had collected. To transfer it, I first froze the nitrosyl chloride in liquid nitrogen. Then I connected the cold trap to a smaller Schlenk flask whose weight I had measured beforehand. Because the nitrosyl chloride was cooled in liquid nitrogen, I could evacuate the entire setup, including the cold trap, without losing any product. If I didn't evacuate the apparatus, I would both condense air and moisture into the smaller flask, and the transfer would take much longer. This is the standard approach whenever you transfer substances under vacuum from one vessel to another by condensation. So I will not mention it separately every time from now on. After evacuating, I removed the dewar under the cold trap and instead cooled the Schlenk flask with liquid nitrogen. It is interesting to see that the nitrosyl chloride, which is a deep red liquid, is yellow as a solid when frozen. Once all the nitrosyl chloride had been transferred into the smaller flask, it was time for the next step, reacting it with the silver trifluoroacetate. This forms trifluoroacetylnitrite and silver chloride. The nitrite is the direct precursor to trifluoronitrosomethane, the blue gas. So I first ground the silver trifluoroacetate into a fine powder in a mortar. This is important because it reacts as a solid with liquid nitrosyl chloride, so a high surface area is crucial. Then I placed the fine powder into a round bottom flask. To transfer the nitrosyl chloride, I connected the two flasks with a hose. Then I cooled the silver trifluoroacetate flask with liquid nitrogen so that the nitrosyl chloride would condense into it. You can nicely see the liquid gas boiling in the Schlenk flask. It almost looks tasty. While transferring the nitrosyl chloride, I prepared a cooling bath by cooling isopropanol to about -20°C using liquid nitrogen. When all the nitrosyl chloride had condensed into the reaction flask, I swapped the liquid nitrogen bath for the -20°C isopropanol bath. That way the nitrosyl chloride melts and can react with the silver trifluoroacetate, but the temperature is still low enough to stop it from evaporating and overpressurizing the flask. I left this reaction mixture at -20°C for about 2.5 hours, occasionally swirling the flask vigorously to ensure good mixing. After that, I needed to get rid of the excess nitrosyl chloride, because it would be a problem in the next step. For this, I connected a second hose, through which I could pass argon through the flask. Then I allowed the flask to warm up to room temperature so that the nitrosyl chloride became gaseous and was carried out by the argon flow. In this way, the nitrosyl chloride was safely disposed of into the into the chemist's bin. Once no orange-red fumes were visible anymore, I assumed that the nitrosyl chloride was gone. When I looked into the flask, there was no liquid visible, only a yellowish solid. So I started to worry that the reaction might not have worked. There was only one way to find out. I connected a new Schlenk flask to the reaction flask via a hose, cooled it with liquid nitrogen, and gently warmed the reaction flask in a warm water bath. After a little while, I saw droplets of a yellow liquid forming in the cold Schlenk flask. So, it looked like the reaction had worked. It turned out though that connecting the flasks with a hose was a bad idea. Even at 125 millibar, trifluoroacetylnitrite still has a boiling point of about 47 degrees Celsius. So it really prefers to condense in the hose and run back into the reaction flask. If I had connected the two flasks with a short glass tube instead, the distance would have been much shorter and I could have simply heated the tube with a heating band to prevent the product from condensing there. With the help of two heat guns aimed at the hose, I eventually managed to transfer most of the product into the second flask. It just took a lot longer than it should have. In the end, I had a usable amount of trifluoroacetylnitrite and I was now only one step away from the blue gas. That last step, however, turned out to be the most time-consuming. If you heat trifluoroacetylnitrite to around 190 degrees Celsius, it decomposes to form trifluoronitrosomethane and CO2. To make that happen, I first have to evaporate the acetylnitrite and then pass the gas through a so-called pyrolysis tube. In this tube, the gas gets hot enough to decompose and the products can then be condensed in a series of cold traps. Unfortunately, the lab did not have a tube with the exact dimensions described in the literature. All their tubes were too long and too wide. Luckily, the lab has a large collection of different glass tubes, which meant I could make my own pyrolysis tube. I took a short glass tube with NS14 joints on both ends, scored it in the middle with a glass cutter, and then used a hot drop of glass to snap it in half. Then I did the same with a longer piece of tube to get a segment of the right length. The plan was to fuse the joints onto the ends of this segment. This lab does a lot of work with quartz, so they have a hydrogen-oxygen torch. It gets much hotter than the propane-oxygen torches I'm familiar with. That's great for quartz, but it took me a while to get used to it. The second fused joint looked better than the first one, but it was still far from beautiful. It did not have to be pretty though, it just had to work. You don't have to be proud of everything you make. With the pyrolysis tube ready, it was finally time to set up the apparatus for generating the blue gas. I connected the tube to a 2-neck flask using a 90-degree adapter. After the tube, I connected 3 cold traps in series. I wrapped the tube with a heating band and placed a temperature sensor between the band and the glass so I could monitor the temperature. Then I wrapped the whole thing in aluminum foil for better insulation. Under each cold trap I placed a dewar. The first dewar immediately after the pyrolysis tube would be filled with a dry ice isopropanol bath to catch easy to condense impurities. The second and third traps would be cooled with liquid nitrogen to condense the blue gas. At least that was the plan. You will see soon why this did not work quite as expected. Under the 2-neck flask I placed a hot plate to be able to heat the flask later. Then it was time to transfer the trifluoroacetylnitrite. People often ask how to transfer air and moisture sensitive compounds from one flask to another. Besides the condensation method you have already seen, using a syringe is another good option. So I connected the flask with the nitrite to the Schlenk line and flushed it with argon. Then I flushed a syringe with argon to remove any air and drew up the trifluoroacetylnitrite. Before injecting it into the flask, I evacuated and flushed the entire apparatus and the flask with argon. One mistake that people often make when emptying syringes, and that really makes my heart race, is not holding onto the needle while pushing the plunger. The needle can pop off and the contents of the syringe will spray everywhere. Depending on what you're transferring, that ranges from mildly annoying to very, very dangerous. Once the nitrite was in the 2-neck flask, I attached a gas inlet tube to the second neck of the flask. Later, I would bubble a gentle nitrogen stream through the liquid to carry the vapor towards the hot pyrolysis tube. I filled the first cold trap with a dry ice isopropanol mixture, the other two with liquid nitrogen, and turned on the heating band. To make sure enough nitrite was carried along by the nitrogen stream, I heated the flask to about 75 degrees Celsius. After a short time, I noticed a serious problem. You cannot see it very clearly on camera, but in the liquid nitrogen cold traps, something was condensing that behaved like liquid nitrogen. In other words, the nitrogen from my carrier gas seemed to be condensing in the cold trap. That is really not what you want. The cold trap would quickly fill up with liquid nitrogen, so there would be no room for the blue gas. And on top of that, condensed nitrogen in a glass system can be quite dangerous. If it warms up even a little and starts to expand, your glassware can explode. This completely confused me. Under normal conditions, nitrogen should not condense in liquid nitrogen. Just like you would not expect water to condense on a surface that is at 100 degrees Celsius. While editing this video, another explanation came to mind. It might not have been nitrogen, but argon. I had flushed the apparatus with argon earlier, and argon does condense in liquid nitrogen. However, at those temperatures, argon would be a solid, not a liquid. So that explanation isn't very satisfying either. If you have any ideas, let me know in the comments. Regardless of what the problem actually was, I needed to find a solution. My solution was to use a different cooling mixture. Liquid nitrogen mixed with petroleum ether. This gets me to around minus 150 degrees Celsius. That is still cold enough to condense the blue gas, but not cold enough to condense nitrogen or argon. All of this took quite a while. Once the setup was finally stable, I could only run the pyrolysis for about 2 hours before I had to stop for the day. By that point, you could already see some greenish blue and orange condensate in the cold trap. I condensed whatever product I had collected into a Schlenk tube. Interestingly, the tube ended up containing far more of a green compound than of the blue trifluoronitrosomethane. Since the gas would generate too much pressure if warmed up to room temperature, I stored the Schlenk tube overnight in a freezer at minus 90 degrees Celsius. When I took it out the next day, you could see a good example of why you shouldn't store flasks with PTFE stopcocks in a freezer. Because PTFE and glass expand and contract differently, these joints are never 100% tight. The blue gas had leaked into the space behind the stopcock. I expected that, so I added a glass stopper with a strong clamp on top, and fortunately none of the gas escaped. I then ran the pyrolysis for the entire next day. Luckily, I could continue working on the first synthesis route at the same time. At the end of the day, I finally had a noticeable amount of a light blue liquid or solid in the cold trap, along with lots of yellow-green impurities. It looks like more than it actually is, but we will get to that later. I also condensed that day's yield into the same Schlenk tube, and to roughly separate the impurities, I made sure to close the tube as soon as there was no blue material left in the trap. At that point, it was clear that my first synthesis route was going to work, and I needed to focus on finishing it. So I decided to not further purify the gas at this stage, but to simply seal it in an ampule. I connected that ampule to the Schlenk tube and condensed the gas into it. I kept the bottom of the ampule in liquid nitrogen while heating the neck to keep the blue gas from evaporating. As soon as the glass softened enough, I removed the dewar and pulled off the top of the ampule. It stays cold long enough that the gas does not have time to evaporate. The result was, as in my previous video, a gas that looks more cyan than deep blue. At that point, I was actually fairly happy. The gas from the other route was beautiful. But as I said in the beginning of the video, over time I became more and more skeptical. And the question became, do I really want to spend a lot of money on a rental car again and drive over 2 hours every day just to resolve this nagging doubt? So, I'm on my way back to Marburg. I just have to know. I can't sleep well without knowing what color this gas really has. So, let's go. But before we get started, I want to tell you about the sponsor of today's video, Radiacode. Radiacode makes radiation detectors that are far superior to a normal Geiger counter. They are not only much more sensitive, but you can also connect them to your phone or laptop to record all your measurements. Using their app, you can combine that with GPS data to easily map the radiation levels over an entire area. And if you do find something interesting, the Radiacode can record a full gamma spectrum, letting you figure out which isotope you're dealing with. I've been using a Radiacode myself for about 2 years now. I've taken it with me while searching for uranium minerals or radioactive antiques at flea markets. If you're interested in getting one, you will find a link in the video description. And now, back to the video. From the previous run, I still had some trifluoroacetylnitrite left. Not much, but maybe enough to make a very clean sample of the gas. For some reason, the nitrite had turned slightly green. I do not know exactly why. Sometimes in chemistry, things just change color for no apparent reason. I rebuilt basically the same pyrolysis setup as before, with one small change. This time I only used 2 cold traps, because in the previous run no trifluoronitrosomethane had made it into the 3rd trap. One general problem with the pyrolysis was that a lot of trifluoroacetylnitrite did not react in the hot tube at all, but simply condensed unchanged in the first trap. So several times I had to stop, warm up the trap and transfer the nitrite back into the 2-neck flask. According to the original paper, they managed to pyrolyze almost 25 grams of trifluoroacetylnitrite in 3.5 hours. I honestly have no idea how they did that. My setup was basically the same as what they described. The only difference is that in their setup they had a 1 mm capillary between the flask and the pyrolysis tube. There are certainly several improvements that could be made to this setup, but at that point I simply did not have the time to redesign the apparatus and optimize the synthesis. So I just kept going. I let the pyrolysis run for 3 days. At the end of each day, I transferred the nitrite back into the main flask and condensed the collected blue gas into a Schlenk tube. What I ended up with was a frozen solid that was again a light blue color, very similar to what I had seen in the first route, starting from trifluoroiodomethane and nitric oxide. There were also a few impurities visible, most likely CO2, unreacted trifluoroacetylnitrite, and nitrogen oxides. The good news is that all of these impurities are quite easy to remove. Either they have different boiling points, or they are water soluble and can be neutralized with a sodium hydroxide solution. To clean the gas, I filled a 2-liter flask with distilled water and added sodium hydroxide to make a 4% solution. Then I let the gas from the Schlenk tube flow into the flask, and as soon as there was no blue liquid left in the tube, I closed it. A yellowish impurity remained behind. I then shook the flask to neutralize the CO2 and dissolve other impurities in the solution. To get the blue gas back out again into a clean Schlenk tube, I first froze the water in the flask with liquid nitrogen. This is a simple way to reduce how much water can evaporate along with the gas. The wall of the flask became cold enough that the blue gas also condensed. And even at this stage, after just one purification step, you can see that the solid or liquid has a very nice deep blue color. After condensing the gas back into the Schlenk tube, you can also see that it looks much cleaner than before. The intensity of the blue color depends a lot on the lighting and on the thickness of the layer. Interestingly, the first Schlenk tube that held the impure sample had turned cloudy. It looks like the glass has been attacked by hydrofluoric acid, which suggests that at least some carbon-fluorine bonds are being broken somewhere in the process. I found that quite interesting. To further purify the gas, I again condensed it into a smaller 250 milliliter flask filled with a sodium hydroxide solution and stirred it vigorously with a magnetic stir bar for 30 minutes. Because the pyrolysis had taken such a long time, I split the purification into two portions. What you are seeing here is roughly half of the total gas I had collected. So yes, the yield was abysmal. At this point, I still did not know if I even had enough gas to fill a 100 milliliter flask to 1 atmosphere. If I did not, all my work would have been for nothing, because then it would still not be clear whether the gas might look more deeply blue at normal pressure. But there was no way around it. I had to keep going. After half an hour of stirring, I condensed the gas into an even smaller, clean Schlenk tube. Even though the apparent color still depends on the layer thickness, you can already see that the condensed liquid is much cleaner and has a deep blue color. Then it was finally time to test how pure the gas is. To check the purity, I recorded an IR spectrum. The sample from my last video still had a noticeable impurity in it, so I was really hoping this new one would finally be clean. To record an IR spectrum of a gas, I need a special cell like this. It can be filled with gas and has diamond windows, so the IR light can pass through the sample. I connected this cell to the Schlenk tube, evacuated it, and filled it with the blue gas. Then I put the cell into an IR spectrometer and started the measurement. As you can see, the impurity that showed up in my previous sample is completely gone. You can still spot a tiny trace of CO2 though. That could either be leftover CO2 in the gas itself or simply a change in the CO2 concentration inside the spectrometer compared to the background measurement. Just breathing next to the instrument sample chamber is enough to give you a CO2 signal. As for the other small impurity, I can't say for sure what it is. It might be N2O, also known as laughing gas, but that's pure speculation on my part. To make sure there was no CO2 left, I washed the gas again with a sodium hydroxide solution. These impurities mean the sample still isn't absolutely pure, but IR spectroscopy is very sensitive even to traces of contaminants. And I don't see any fraction with a boiling point different from the blue gas itself. So I'm confident that whatever impurities remain are minimal. Since I only had a very small amount of the blue gas left and not enough time to make more, I decided to not chase down those last traces of other compounds. But I genuinely encourage anyone to repeat the synthesis and either confirm or disprove the results I'm about to show you. After washing the gas again, I condensed it back into the Schlenk tube, and it was finally time to seal the gas in an ampule to see what the color really looks like. But there was one small problem. That tiny puddle of liquid at the bottom of the Schlenk tube was all I had left. I really did not want to risk putting it into a 100 milliliter flask and then discovering that it wasn't enough to reach 1 bar inside. That would have wasted the only pure sample I had. So instead, I decided to use a smaller ampule with a volume of about 40 milliliters. A huge shout out to the glassblowers at the university for making this for me on such short notice. And of course, a huge thank you to Professor Kraus and all his PhD students for letting me perform these experiments in their lab. I connected the ampule to the Schlenk tube, evacuated it, and condensed the blue gas into it using liquid nitrogen. Then I fixed the ampule in a dewar so that the bottom stayed cold, but I could easily reach the neck with a torch. Because of the vacuum in the ampule, the glass neck collapses inward as I heat it. I moved the flame around the neck until it was fully sealed and then slowly pulled off the upper part. By the way, if you enjoy videos like this, I would really appreciate if you subscribed to the channel or even became a channel member or Patreon. The link is in the video description. Every cent of your support goes directly into videos and projects I am working on. So, from the bottom of my heart, thank you to all my channel members and Patreons. After sealing the ampule, it is important to let the hot glass cool down slowly in a sooting flame. That helps release internal stress in the glass and reduces the risk of it cracking later. And now, finally, it was time for the moment I had been working toward this whole time. Letting the ampule warm up and seeing what color the gas really has. As the gas warms up and starts to evaporate, it initially looks very similar to the sample from my previous video. But not all of it has evaporated yet. Once more of the gas goes into the vapor phase, the color becomes clearer. And honestly, that is a beautiful blue. At this point, I think we can safely say that this is a blue gas and not a cyan one. You can argue about whether it counts as deep blue or not. Personally, if I had been the first person to ever make this compound, I would have called it deep blue, especially for a gas. Compared to my previous sample, you can clearly see the difference in color. When you freeze it, the solid or liquid is absolutely a deep blue. Because some people asked in the last video, I also recorded a UV vis spectrum of the gas. But there is still one important question left if we really want to be sure that the gas does not suddenly look darker at higher pressure. Does the ampule actually contain at least 1 bar of pressure? If it does not, then everything I have done still leaves open the possibility that at 1 bar the color might be different. To test this, I used a simple method. The gas has a boiling point of about -85°C at 1 bar. So if I put the ampule in an isopropanol dry ice bath at -75°C and see a liquid forming inside, then the pressure in the ampule must be greater than 1 bar. Otherwise, the gas would not condense at that temperature. And when I cooled the ampule to -75°C, you can indeed see a small puddle of liquid forming. So yes, the pressure is at least 1 bar, and this is what the gas really looks like under those conditions. I cannot tell you how relieved I am to finally be able to upload a correct picture of this gas to Wikipedia. The only way to make it look even darker would be to increase the path length. In simple terms, make more of the gas and put it into a big flask. Then you would probably get an even more intense deep blue color. But that is not going to be me. I think I've had enough trifluoronitrosomethane for now. I really hope you enjoyed today's video. Other than that, thank you a lot for watching.